Well, hello there. Today we're talking about randomized algorithms. So the main motivation of this area is that you want to solve a problem like in a really fast fashion. It's usually okay to have not the best possible solution as long as it's fast. And usually you're not, your problems at least in the real world, you're not dealing with some like life and death situations, in which case please don't use randomized algorithms. But if the price of the mistake is rather small, you can balance it out with increase of your performance that is just would be too good to pass on, right? So randomized algorithms could be of several different kinds. One is they all have the same thing in common. They use additional source of randomness that allow them to do things with input that are not determined by the input, right? So yeah, they can do random things to the input. That's the name randomized algorithms. So one thing a randomized algorithm can do is we can define them so that they can give us wrong answers sometimes, right? So sometimes they can fail and just straight out give us incorrect answer. Another type would be when sometimes they just fail to give us any answer, right? So let's say we can define an algorithm that with probability 10% will just refuse to give us anything. So that's also a way to give algorithm a slack, right? So if we want to have this model with like better performance, we need to give it some reasonable ability to fail. And so we discussed you can just give wrong answers, you can not give answers at all, or you can give answers in rather unpredictable time, right? So the last one is very common, where your performance typically is really good, but sometimes you can take a really long time for your computation. So your resource management is randomized rather than the actual answer. All right. So let's start with the first type, the algorithm that could fail. So here is a fun problem. Polynomial identity testing. Okay, input. An arithmetic formula. Of length n. And let's say our formula can have it could consist of addition, multiplication, constants, the name of the variable, or brackets. That's all we can have. So for example, something like 1 plus x times 3 minus 2 times x plus 3 bracket minus x plus 1 times 1 plus 5 plus 3. That is a valid formula, right? So, and the output, yeah, you can have, you can define minus, I just realized that my multiplication and x look exactly the same. So let me write x in a different manner. Okay. So what are we interested in about this formula? The answer, the question looks rather silly, but it's surprisingly important question. So, is it 0? Is it equal to 0? So, a good example of a formula that give us something that is actually 0 would be, for example, x times x plus 1 minus x plus 1 times x minus 1. So it's just an example that sometimes you can have these formulas that are not, I mean, you probably, whoa, sorry about that. That should be a minus, right? So that would be, am I right? Yes. So that would be a formula that is actually equal to 0. So there is a rather trivial algorithm, right? How can we solve that? Well, we can just go through the formula and expand all the brackets. So I can take this and turn it into x times x minus 1 minus, and then I just do this multiplication, which would give us x times x plus x minus x plus 1. And then just cancelling out the terms, I will get 0. So just go through the formula, find the most inner brackets and do stuff with them, and then repeat until you get a formula that is just sum of the incomparable terms. And if you have those terms that are not 0, then, well, you know the answer to your question. So what is wrong with this algorithm? Why I am not happy about it? Obviously. Well, let's consider an example to see what can go horribly wrong. So here is a formula. So we have x plus 1 times x plus 1 times x plus 1 and so on times x plus 1. So the whole thing when you expand it, like when you do all the multiplications, will result in, so if you had k brackets, so if you had k terms that you multiply together, then you will have formula of, right, so x to the k plus k times x to the k minus 1, and so on. So this is not too bad, but in the process you can get up to exponential number of different terms. So expanding those things could actually take you a really long time. So what would be the easier way to do that? So one way to do this is to say, hey, if this polynomial is 0, if this polynomial is actually identically equal to 0, then if I plug in any number instead of x, if I plug in absolutely any number instead of x, and compute the value of this formula, I will get the same number. I will get just 0, right? So this gives rise to this very cute algorithm, which is just take a random number. Well, it's not too big. Just pick just a moderately sized random number and plug it instead of x, and compute the value of the formula. After you do that, check if it's 0, then you're good, and if it's not 0, then you know for sure then your polynomial is non-zero, right? So my question is it possible, right? Is it possible that I will fail? So of course it's possible. Of course it could be that my polynomial is non-zero. My polynomial is non-zero, but after I picked a random number, this formula results in 0. That's because I accidentally picked a root of this polynomial, right? So how could I bound the probability? So the question is it likely? Is it going to be a problem, right? So how we know that sometimes I will give you the wrong answer because I accidentally picked a root of the polynomial that is not equal to 0, but now I think it's 0. So obviously we have to bound that probability. So if our algorithm is pick a number between 1 and m, so and then use this number, so pick a number r, and then use this number, so compute. So if our formula, an arithmetic formula f, so let's see, if we compute f is f of r equal to 0. So this is what we output. Our formula has length n, which means that the maximal possible degree of the polynomial f is n, right? we know from algebra that any polynomial of degree at most n can have at most n roots. So probability that f of r is equal to 0. So is at most n over m if f is not actually identically 0. So as long as we pick m to be large enough to be, let's say, so we can pick m to be like 100 times n, and then we will be wrong at most 1% of the time. Or we can pick it 1 million times n, and then we will be wrong 1 over million, 1 in a million times, which is, you know, the larger you pick m, the more expensive your arithmetic calculations become. And this is a very typical trade-off. You can have a faster algorithm when you allow, like, when you give the algorithm more slack. If your algorithm allows to fail more, then it can get faster. Obviously, if we go this route and just decrease the error just all the way to 0, we will go to the deterministic algorithms, and that is not what we want. So we actually want to allow algorithm to fail sometimes, otherwise this whole technique is pointless. So yeah, just by picking m large enough so we are not bothered by the frequency of the mistakes, we will get our algorithm that runs in linear time, because all we need to do is just to compute the formula on a random number, which can be done in linear time. All right, so now we will move on to another example. So we would like to solve a problem, and the algorithm we will discuss it will always return the right answer, but the time it will spend finding it will be not determined, right? So it will be not deterministic. It will typically run in a very efficiently, but sometimes it can run basically as long as it wish. So the question we are going to discuss is the median problem. So input and so as input you're given n numbers, right? So you're given a1 through an, and the question is output so you need to output the median, so you need to output aj such that n over 2 out of n a's, so ai's are less or equal to aj. So you need to find an element that if you sort all those numbers by value would be right in the middle. So that That is the question. We would like to do that in linear time. So sorting, so one way to do it would be to sort the numbers, and we haven't discussed how to do that, but you can sort the array of numbers in time around n log n. So we can do that, but that is too long. So I want to do it in time linear in the size of the array. All right. There is in fact a deterministic algorithm for that. It is both complicated and just slower in practice than what we will discuss now. So this is actually the algorithm that people are using. It's not, you know, a party trick. All right. So you have your array, all right, and we want to find the median. So how could we do that? So, well, we want to do it like round by round, and each round we want to cut a piece of this array and say, hey, median is not here, and just throw a bunch of elements away. So at the beginning I'm looking for the median, so I'm looking for the element that in a sorted, if I sort A1 to AN, will be on the place n over 2. I want my algorithm to do something like this. I want then to say, hey, those guys are not are all to the left of the median, so I can throw them away. And now I'm looking for the element over here. It's not in the middle anymore. And I know that, like, for example, this is n over 6. Right? Then I find another bunch of elements, let's say here, and say, hey, they're all to the right of the element I'm looking for. So let's cut them also, right? So then I will have something like this. So every round we will find a bunch of elements that are definitely not the median. We will throw them away. We will adjust what the position in the array we are looking for, and we will continue. So how do I do this? How can I say that all those guys are to the left of the median, and so I can throw them away? Well, let's say I know some number that is to the left of the median. Just any number to the left of the median. Then what I can do, I can go through my array and find all the numbers that are smaller than that number. So if you're smaller than the number that is smaller than the median, that you're also smaller than the median. So that means that I find a bunch of numbers that are smaller than my boundary number, and that means that I can throw them all away and just readjust the position of the median. The question is, how can I get this number? So, and what will make this number good? So the nightmare scenario right? I'm looking for a median, and I want a number that is smaller than the median, so I can do this trick, right? So if I'm getting the number over here that is just smaller than everything in my array, then it's useless. It's not throwing away anything in my array, so it's not shrinking, so it's like literally nothing happens. So this is not good. Okay, what else is not good? Well, if I pick a number somewhere here, so this is, there are only a few numbers that are smaller than the boundary. That is also not great. So I want first of all, I want this boundary to be at least useful at all. So I need it to be inside the range of my array. And then I want that probably, this one I won't be able to guarantee, but probably it's cutting away more than a few elements. Probably, with high probability, it's cutting away a portion of my array. Let's say at least 10%. So my array is shrinking by 10% every round with high probability. So how can I guarantee both of those things? Well, I can pick a random element. I can pick a random index I and say, hey, let's pick AI as my boundary element. So it might end up to the left of my target element, of my median at first, and then some target element. Or it can land to the right. I will go through my array and I split, so yeah. So I have my array, and right now it's just a bag with elements. There are no order. So I always write them, I always draw them as an array, but that's imaginary thing, right? I don't store them like that. If I had time to put them in order, I would have been done. But I have them in a bag, like this. So what I do, I pick a random one. So I pick AI, random AI. All right, and I use that AI to split this bag into two things, right? So those who are more than AI and those who are less or equal to AI. So those clearly two different possibilities. There was nothing else that can happen. So I have my bag split into two these sub-bags, subsets. Okay, cool. And now I know the sizes of them. So one of them is containing my target element. On the very first step, the one that is larger contains my target element, my median, right? Then our definition of target element will shift from the median to, some element at the concrete position, and then this concrete position would be either in range of this subset or not. So I know that it will belong to one of them. So I know which one I can just discard and say, hey, I don't want you. I don't. So let's say that this set at the beginning turns out to be smaller than n over 2, then I just can go and only with elements that are larger than AI and just discard the lower half. Okay, I'm not interested just done with them. So now the only thing we need to understand is that with high probability, this thing would be, let's say, at least 10% of the whole array. Again, we don't have time to actually go through the basic of probability theory. I hope you will catch up with other classes on that, but when you're picking a random element, it's highly unlikely that you will end up in the, like, let's say, top 10% or lower 10%. You have, like, most of the time, you will end up somewhere in the middle. So with probability, let's say 70%, I'm just making up numbers up, but with high probability, not overwhelmingly high, but with high probability, constant probability, you will actually chop off a concrete portion of your input. And then you just repeat, and you will get your array getting smaller and smaller and smaller, and eventually it will get down to just one element, which would be the element you actually need to output. All right, so again, I don't want to go through very thoughtful process of calculating the running time of the thing, but what is a little bit counterintuitive about it is that you have a bunch of steps. Each step, so you lose like a portion every time, so you can expect around log n, like that number of rounds would be proportional to log n. Then for each of them you will need to do this splitting in half, which obviously takes linear time because you need to scan through the whole array, right? So if you look at this, you can say, hey, even if you did split like in half every time, so if you're even lucky every time, it still looks like it will take n log n, but that is not the correct way to think about it. The point is that our inputs are shrinking. So every next one will take less time on the splitting than the previous one. And actually, if you sum them all up, I know that it's log n of them, and the longest can take up to linear time, but that's a very crude estimate. If you do that in actually accurate manner, you will get that the whole thing takes about linear time. Well, just linear time. So then you need to say, hey, sometimes I can get very unlucky. And my splits would be very, very unbalanced. So again, we don't have time or machinery to go through the calculation of the probability, but chances that it will take like more time than twice the average are quite low. So yes, you can get bad splits, but you'll probably get you'll probably get a constant portion of your splits to be bad. That means that you will have like not log n, but like log n times 2. That's like the top of what you expect to be like if you're like reasonably unlucky. And of course, if it can get forever. We can, in the worst case scenario, we can cut off one element at a time, which will bring the running time to like n square, I guess. But that seems nearly impossible in terms of probability. So that's the algorithm for the median problem.